Hello guys, this is Praveen and welcome back to my channel. Today we will solve more GATE PYQs on the topic Greenshield Model, which is a part of traffic engineering in the subject Transportation Engineering. But before jumping onto the new questions, I will give you a quick review of the questions which we did in the part 1 of this series. So now I will switch on to the whiteboard. As you can see over there. We started the part 1 with the revision of the important formulas of the Greenshield model. What were those? The first one was the relationship between speed and density, V is equal to Vf 1 minus K by Kj. Second one was the basic flow equation, Q is equal to Vk. Third one was the simply substitution of this velocity into the basic flow equation. We got the relationship between flow and density. It was parabolic because Q is proportional to K square. And when we differentiate this flow with respect to density, we get a density is equal to half of Kj. And at this density, the flow is simply Qmax, that is the maximum flow possible, and it is equal to 1 by 4 Vf Kj. And this Qmax is also known as the capacity of the road. And also if we put this density K equal to half Kj into equation 1, we will get a velocity, or you can call the speed as half of Vf. Then we had two more basic formulas, the one relating the density with the space headway, K is equal to 1000 upon S, and the second one relating the flow with time headway, Q is equal to 3600 upon H, where H is in seconds and S is in meter. Then we started the first numerical. It was direct formula based question and it was quite easy. The second question was a graphical question, we solved this. The third question was about establishing relationship between flow and density plus flow and speed. And guys, we are going to use this relation in later part of this video, because we're gonna need this relation between flow and speed, which is equal to Q is equal to V Kj minus V square Kj by Vf. And since we have already derived it in the part 1 of this series, so I will be simply directly using this formula and I will copy it from here and paste it over that question. Then we had this question number 4. It was about the speed of the shock wave, and the speed of the shock wave is given as change in flow upon change in density. It was direct formula based question. Then we had this question number 5. We solved this question by two methods. The first one was the option approach and the second one was the graphical method. The question number 6 was simply direct formula based question. They asked the speed at the maximum flow and it is simply Vf by 2. So if you remember the relations, you can solve it without even deriving anything. And yeah, this question number 7. I told you in the part 1 that this question is special. Now we will know in this video that why this question is so special. Although it's not very difficult, but I skipped it in part 1 just for this part. So in few minutes you will know why this question is so special and I had to skip it for this part. Then we solved question number 8. It was a good question in which the flow density relationship was given like this and they were asking the speed density relationship. We solved this question by separating the graph in two portions, AB and BC. We will be solving a similar question in this video as well, but that question is simply the inverse of this question. Why? Because in that question, speed density relationship will be given and we need to find the flow density relationship corresponding to that graph. Okay, and we will be using the same approach which we used in this video. And then we had this question number 9, direct formula based question, and quite an easy question. Plus this was also the last question of the previous video. That means we are left with question number 10, and this is the first question of this video. So let me zoom in to a proper level. Yeah, this much is fine, I think. Okay, so I will read the question now. The speed density relationship of a mid-block section of a highway follows the Greenshield model. If the free flow speed is Vf and the jam density is Kj, the maximum flow observed on this section is, again for Greenshield model, the maximum flow Qmax is simply 1 by 4 Vf Kj. So the correct option is option C, direct formula based question. And a similar question was asked in 2011 as well, but that time it was of 2 marks. That time they asked if the jam density is given as Kj and the free flow speed is given as UF, the maximum flow for a linear traffic density model is given by which of the following options. They didn't say that it's a Greenshield model, but they did tell us that there is a linear traffic speed density model. That means they are talking about Greenshield's model. And for Greenshield's model, the maximum flow is given as 1/4 VF Kj. So the correct option is option A. Both are exactly same question, only the language of the question was different. Moving on to the next question, we have question number 11. So the question says, average free flow speed and the jam densities observed on a road stretch are 60 km/h and 120 vehicles per kilometer respectively. For a linear speed density relationship, the maximum flow on the road stretch is, again, direct formula based question. We know that for a linear speed density relationship, that means Greenshield's model, the maximum flow Q max is simply 1/4 VF Kj. VF is given as 60 and Kj is given as 120. So directly putting in the values, 1/4 into 60 into 120. This will cancel out as 30, so it will be 1800 vehicle per hour. So the answer is simply 1800. Very easy question, formula based, and it was 2 marks question. Then moving on to the next question, we have question number 12. The question says the space mean speed km/h and the density vehicles per kilometer of a traffic streams are linearly related. The free flow speed and the jam densities are 18 km/h and 100 vehicles per kilometer respectively. The traffic flow in vehicles per hour up to 1 decimal place corresponding to a speed of 40 km/h is, again, linearly related, means it's a question of Greenshield's model. And what they are asking the traffic flow corresponding to the speed of 40 km/h. That means we need a relationship between flow and speed. Now remember what I said in the question number 3, that we are going to use that relation because we have already established this relation between flow and speed. It was in question number 3. I will show you. Yeah, over here. This was the relation between flow and speed. So I am not deriving it again. I will simply copy it from here. And paste it in our current question. Over here. So this is the required relation between flow and speed. Now I will directly put on the values. Q is given as, Q we need to find out. Q is equal to V is given as 40, Kj is given as 100, so 40 times 100, minus V square means 40 square, Kj 100 by Vf is given as 80, so divided by 80. Simplifying it, we will get 4000 minus 1600 times 100 upon 80. This will cancel out by 20, so 4000 minus 2000, which is equal to 2000 vehicle per hour, and this is the answer, 2000 vehicle per hour. Nothing special in this question except this relationship, and we have already established this relationship in question number 3, and we solved that question in part 1 of this series. Now moving on to the next question, we have this question number 13. Yes guys, this is the question I was talking about, that this question is simply the inverse of question number 8, which we already solved, and it is again the graphical question. They gave us the speed density relationship and they are asking the flow density relationship. Okay, so again I will use the same approach which I used in question number 8. I will divide this graph in 2 portions. First is AB, second is BC, and then we will analyze both these portions separately. So I will first analyze the portion AB. So I will write it over here AB. Now we will use two basic equations. The first one is the standard equation of a straight line, that is y is equal to mx plus c. And the second one is the basic flow equation, q is equal to vk. And let us number this equation as equation number 1. Okay, now let us look at the graph. Here the x-axis, x is simply the density k and y is simply the speed v. Okay, so for the portion AB we have y is speed, v is equal to m, which is slope. What is the slope of line AB? 0, because it is horizontal. So 0 times x is k plus c, intercept is c. This length is c. Okay, and this is the origin. So that means we have speed v is equal to c, and c is nothing but constant. Let us call it as equation number 2. Now putting the value of speed from equation 2 in equation 1, we will get from 2 to 1, we will get q is equal to v is constant, times k. That means we can conclude from this relation that q is directly proportional to k to the power 1. That means they both are linearly dependent in the portion AB. Okay, now portion AB is done. We have to solve the portion BC now. So I will analyze portion BC over here. Again, we have to write the equation of this line BC. Again, y is equal to mx plus c. Here y is v, m. What is the slope of this line? Let's say the slope of this line is simply m. Okay, and the intercept, y-intercept. How are we gonna find it? Simply extend this line backwards like this. Suppose it is cutting the y-axis at this point. So this portion is the y-intercept. Let us call it at C1. Okay. So the equation for the line BC will be v equal to m, x is k plus c. Let us call it as equation number 3. Now from equation number 3, put the value of speed into the equation number 1. That is, we know that the equation 1 was q is equal to vk. Put this relation into this equation, we will get q is equal to mk plus c times k. Okay, expand it, we will get q is equal to mk square plus ck. And we can already say by looking at this equation that the flow is directly proportional to k to the power 2. That means it's a parabolic relation. Okay, so from these two analyses we can conclude that in the portion AB the relationship will be linear between flow and density, and then in the portion BC the relationship will be parabolic. So the correct option is option C, initially linear and then parabolic. Okay, and it was asked in 2018 SAT 1 marks. Then moving on to the next question, we have this question number 7. Yes guys, this is the question which I skipped in part 1 of this series. And why I skipped it, now you will see. Because this exact question has been asked 3 times already. Even they didn't even change the numerical values. The answer of question number 14 and 15, even they are also the same, and it's a numerical answer type question. And this makes this question really special. So I'm gonna read the question. First we will solve the question number 14 and 15. The question says, let us read question number 15 because both of these are same. The speed density relationship on a single lane road with unidirectional flow is given by this equation. Let us call this equation number 1, where u is in kilometer per hour and k is in vehicle per kilometer. The capacity of the road in vehicle per hour is. By looking at the equation 1, we can see that the speed and density are linearly dependent. That means it's a question of Greenshield's model. And for Greenshield's model, we know that v is equal to vf minus vf by kj times k. Let us call it as equation number 2. And by comparing equation 1 and equation 2, we can directly conclude that VF, the free main speed, is simply 70 km per hour, and the ratio VF by kj is equal to 0.7. Okay, put this value from here to here, we will get kj is equal to 70 upon 0.7, which is simply 100 vehicle per kilometer. Okay, so we got both the values, we got VF and we got kj. So we can find the capacity of the road. Capacity is nothing but maximum flow, Qmax. And for Greenshield's model, Qmax is simply 1/4 VF kj. Now put these values of VF and kj in this formula, we will get 1/4 times VF is 70 and kj is 100. This will cancel out as 25. Now I will use the virtual calculator which they will be providing in the GATE examination as well. So I will switch on to the virtual calculator, as you can see on the screen. So 70 times 25, it is 1750. So the answer is 1750 vehicle per hour. I will remove the calculator now. So the answer for question number 15 is 1750, and also for question number 14, 1750. Okay, and because in both the question they were asking the capacity and capacity. Okay, now let us go back to the question number 7. This question is also the same, but except the capacity, they asked that at capacity condition what is the average time headway. Okay, so we will use the relation between flow and time headway as Q is equal to 3600 upon H, where H is the time headway. That means at Qmax it will be 3600 upon H. That means H is simply 3600 upon Qmax. What is Qmax? We just calculated as 1750. Okay. Now again I will use the calculator to find this ratio. This is the calculator. So 3600 divided by 1750. It comes out to be 2.057. 2.057. And if we round it off to one decimal place, we can round it off to 2.1 second. That means the correct option is option C. Let me remove the calculator now. Yes. So the option C. See, both these three questions are same because the equation of the line between speed and density were also the same in all three questions. And first we need to find the capacity and then this headway. Okay. Now moving on to the next question, we have question number 16. On a section of a highway, the speed density relationship is linear. Again, linear means Greenshield's model, and is given by this equation: V is equal to 80 minus 2/3k, and I am numbering this equation as equation number 1, where V is in kilometer per hour and k is in vehicle per kilometer. The capacity of this section of the highway would be, again we know that for Greenshield's model we have V is equal to Vf minus Vf by kj times k. Comparing equation 1 and 2, we can conclude that Vf is equal to 80 and the ratio Vf by kj is equal to 2/3. Put this value 80 over here, we will get kj is equal to 80 into 3/2. That means kj is equal to 120 vehicle per kilometer. And Vf is already known, so they are asking the capacity, means Qmax. So the Qmax is simply 1/4 Vf. Vf is 80 and kj is 120. This cancel out as 30. So this will be 2400 vehicle per hour. So the correct option is option B. Direct formula based question, very easy question and 2 marks, asked in 2021. Moving on to the next question, we have question number 17. So the question says, a two-lane urban road with one-way traffic has a maximum capacity of 1800 vehicles per hour. Under the jam condition, the average length occupied by the vehicles is 5 meters. The speed versus density relationship is linear. For a traffic volume of 1000 vehicles per hour, the density is, so they gave us the traffic volume Q and they are asking us the density K. Okay, what else they have given us? They have given us the capacity as 1800 vehicles per hour and they gave the average length or the space highway under jam condition as 5 meters. So let us first calculate the unknowns. Q max is given as Q max for 2-lane. Remember this. The question is for 2-lane road. For 2-lane is given as 1800 vehicle per hour. The second thing is average length. That means if we use the relationship between density and space highway, K is equal to 1000 upon S. So at jam condition, it will be Kj is equal to 1000 upon S. What is S? It is 5. So it will be 200 vehicle per kilometer. Now there is one thing to notice over here. This jam density Kg is equal to 20 vehicle per kilometer is for single lane road. Single lane road. Because that's how this formula was derived. It was derived for one lane. But the given lane in the question is 2 lane. I mean the given road is 2 lane road. So we need to convert this density for 2 lane road. How are we gonna do that? We will take an example to understand how it works. Suppose we have a road stretch of length 1 kilometer like this. Its length is 1 kilometer. And suppose it is in jam condition. Jam condition. Okay. That means there will be certain number of vehicles occupying this road. Let us say there are 1, 2, 3, 4, 5 vehicles under jam condition in a 1 kilometer stretch of road. So this 5 will simply be the jam density of this road, because jam density is nothing but number of vehicles occupying 1 kilometer stretch of a road under jam condition. So its density will be 5 vehicles per kilometer. Now suppose there is one more lane. So I will simply copy this lane and paste it below it. So what will happen? 5 more vehicles can occupy one more lane, and that is, I will write it over here, 5 vehicles per kilometer for another lane. So what will become the total density, total jam density of this combined road? It will be simply 5 plus 5, 10 vehicles per kilometer. And this is the jam density for 2 lane. Okay, the vehicles simply occupy one more lane, and because only 5 vehicles were occupying one lane, 5 more vehicles can occupy another lane. And if there were 3 lanes, then 5 more vehicles will occupy that lane, and the density will become 15 vehicles per kilometer for 3 lane. But we are stopping at 2 lane. That means the jam density for 2 lane will be simply twice the density of 1 lane. Okay, and we will use this relation to find the jam density for the 2 lane road given in our question. So the jam density, I will use the blue pen. Jam density for 2 lane will be equal to 2 times the jam density of 1 lane. What was that density? 200 vehicle per kilometer. So 2 times 200. That will give us 400 vehicle per kilometer. Okay. Now back to equation number. No, there was no equation. So we got Kj, we have Qmax. So we can find the free mean speed. How? From this formula, we have Qmax is equal to 1 by 4 Vf Kj. Okay. Qmax for 2 lane road was given as 1800 is equal to 1 by 4 VF we need to find, and KJ for again 2-lane road is 400. This will cancel out as 100, 0, 0. That means the free flow speed is 18 km per hour. Okay. Now for Greenshield's model, we know that Qmax is simply 1/4 VF KJ, and Q, the relationship between Q and density is VF 1 minus K by KJ times K. Divide these two relations. We will get Q max by Q is equal to VF will cancel out. We will be left with KJ upon 4 1 minus K by KJ times K. Now put the values in this equation. We will get Q max was 1800. The flow at which the density is required is 1000 is equal to KJ was 400 divided by 4 times 1 minus K by 400 times K. This will cancel out. This will be 100. So resolving it, we will get 18 upon 1000 is equal to, multiply K inside, we will get 1 upon K minus K square by 400. That means cross multiply K minus K square by 400 is equal to 1000 upon 18. Multiply both sides by 400, we will get 400 K minus K square is equal to 1000 into 400 by 18. Rearrange this equation, we will get our final quadratic equation, K square minus 400 K plus 1000 into 400 upon 18 is equal to 0. Now we need to solve this quadratic equation to find the densities. So I will use the quadratic formula, that is K is equal to minus of minus B plus minus under root B square, that is minus 400 square, plus B square minus 4 AC. C is 1000 into 400 by 18 divided by 2A. A is simply 1, so divided by 2. First I will calculate this big bracket so that we can handle it properly. Again I will use the virtual calculator, so I will switch on to the virtual calculator over there. So we need to calculate 400 square minus 4 times this number. So 400 square minus 4 times 400 into 1000 by 18 bracket close. This comes out to be 7111, and then take the square root. It is 266.67. That means K is equal to, I will use the blue pen, K is equal to 400 plus minus 266.67 divided by 2. This will give us two densities, K1 and K2. Again I will use the calculator to find K1 and K2 both. So 260 plus 400 divided by 2. The first one is 333.33. Vehicle per kilometer, and the second one will be 66.67. That is 66.67 vehicle per kilometer. Why are we getting two densities? Because I will remove the calculator now. Yeah, why two densities? Because we know that in Greenshield's model, the flow and densities are related by a parabolic equation. That means here it's density, here it's Q. So the graph goes like this. The graph goes like this. It's parabolic. Okay. At the end point, it is the jam density, and this topmost point, it is the Q max. For any value less than Q max, suppose this value 1000, we will get two values of the densities, as you can see over here. First one is K1 and the smaller one is K2. This is K1 and this is K2. That's why we are getting these two densities for one flow of 1000 vehicle per hour. Okay, both these densities are correct, but let us see what the options are provided. So in the option, only 67 is provided. 67 is nothing but the round of 66.67. So the correct answer is 67. Okay, it was asked in 2012, 2 marks. Moving on to the next question, we have question number 18. And the question says, a linear relationship is observed between speed and density on a certain section of a highway. The free flow speed is observed to be 80 km per hour and the jam density is estimated as 100 vehicles per kilometer length. Based on the above relationship, the maximum flow expected on this section and the speed at the maximum flow will be, again, direct formula based question. The relationship is linear, means it's a Greenshield's model, and for Greenshield's model we know that the Q max is simply 1/4 VF kj. VF is given as 80 and kj is given as 100. So directly put the values. VF is 80, kj is 100. That means the Q max is 2000 vehicle per hour, and we saw in the beginning that Q max occurs at a speed of half of VF. That is, at Q max the speed is half of VF. That means 1/2 times 80. That means 40 km per hour. So the answer is D, option D, 2000 vehicle per hour and 40 km per hour. Direct formula based question, very easy question. Now moving on to the next question, we have question number 17. No, this is actually question number 19. There is a typing mistake over here. Yeah, question number 19. The question says, on an urban road, the free mean speed was measured as 70 km per hour and the average spacing between the vehicles under jam condition is 7 meters. The speed flow density equation is given by this equation. The maximum flow per lane for this condition is. Again, by looking at this equation, we can directly conclude that it's a question of Greenshield's model. And for Greenshield's model, the maximum flow Q max is nothing but 1/4 VF kj. VF is given as 70, but kj is not given. But to find kj, they gave us the spacing, that is the space had by under jam condition, as 7 meters. So I will use the relation k is equal to 1000 upon s. So at jam condition, it will be kj 1000 upon s. S is 7 vehicle per kilometer. Now put this value in the formula of Q max. We will get Q max is equal to 1/4 times VF is 70 and kj is 1000 upon 7. This is 10, this is 250. So Q max will be 2500 vehicle per hour. So the correct option is option B. This question was asked in 2006, 2 marks. So this question was the last question of this video. I hope you liked it, and if you have missed the part 1, you can watch it by clicking over the link. Until then, Keep going.